The AWG is driving two signals out. One is the actual signal on channel 1 of this AWG that is driving the channel 2 input of my scope. It's terminated to 50 ohms, so you get a fairly clean edge without any reflections. And channel marker of the AWG drives channel 3 of the scope. So together we can see there is already some delay between these two because of connectors and mismatch in the cables. They're supposed to be identical cables over here, but because of the differences in the terminations and as well as the connectors, there's going to be some delays. So the actual delay difference now between these two signals, which ideally should be 0, is 21.55 nanoseconds. So I'm going to make a note of that, and then I'm going to connect an additional 3 feet cable on channel 1, so you get to see the delay of a 3 feet cable. So let's do that next. So here I have spliced in an additional section of a 3 feet cable with a connector, so there's going to be some extra delay, of course, with this connector in there, but let's assume it's fairly short, and maybe a few hundred, 50 picosecond, whatever it is. But we look at the delay. Theoretically it should be around 3 feet for the 3 feet cable. So let's move the marker cursor and see where that's moved to. So the new delay with the additional 3 feet of cable is now at the center would be around 26.7 nanoseconds. So now we take the difference between these two. That should give us a delay of this extra 3 feet segment. The next method I'm going to try to measure the delay in a cable is going to be using a vector voltmeter. This one is an HP8405A, a fairly old instrument. I think it's a precursor to the network analyzers of today, and you can still find them around fairly cheap on various online websites, eBay and so on. It's a bit weird to use, and you need special jigs to actually do some of the measurements that call for to access the signals. As you can see, this is a probe. There are 2 probes for this one. I'll explain a little bit more as I demonstrate this. So the probe A is basically used as a reference, and that's this one. It's used to basically lock to an external signal, like a sinusoidal signal from a source, and B is the actual received signal that is comparing with the reference. So what I have on top is a RF signal generator that is generating 20 megahertz at minus 30 dBm, and that's being applied to the vector voltmeter. There's a special jig for that, and I will show you that now. As you can see, the jig on the table, there's a power splitter in the middle which 20 megahertz comes into, and it distributes the signal onto both sides, and is terminated 50 ohms at the end on both sides, so there's no reflections. I put the channel A, which is a reference, into the port 1 over here, and I'll put the received signal on port 2 on the right side. Since these two sections are equal in length and they are matched in, mechanically matched in all respects, the signal that enters here splits into 2 and basically enters the channel A and channel B of the vector voltmeter, and is terminated, so there are no reflections. So whatever enters basically is terminated and fed into the channel A and channel B respectively. As you can see right now, there's no the vector voltmeter is not locked. It's a frequency sensitive instrument, so I got to bring the frequency range to approximately the frequency that is being transmitted by this RF signal generator. So we're going to do that, and it will actually lock over a fairly wide range, so it's already locked, as you can see. But I'll just bring it to 20, which is a frequency that I am interested in, and just use it at this setting. Now the APC light is says unlocked, is gone. That means it's locked. And you can see it on channel A, the amplitude is in the minus 30 dBm range, and you can compare the signal on both A and B, and they should be equal because there's no differences in the length of the cable or in this section, and A and B ideally in a well calibrated instrument should be about the same. So as you can see, there's no difference in the amplitude on channel A and B, and the phase difference actually it's already set at 0 and nulled to that, so it's right now at 0 degrees. So that is a perfectly equal signal on both channel A and B. There's no phase delay, there's no mismatch in any way. So now if you introduce a delay on one side, you should be able to measure the phase difference and also the amplitude change on channel B. Channel A is going to remain the same, terminated to 50 ohms with no difference. So now let's introduce that same 1 meter cable in this section. So whatever enters here will pass through that cable, and then that delayed signal will appear on channel B only. Right now I've connected this 1 meter cable in between the two sections here. As you can see, they are now separated, and now we'll look at the signal on channel A and channel B on the vector voltmeter right here. Now as you can see, the phase has changed quite a bit, so it's basically not in the range it's supposed to be because of the phase delay. So now we'll try to measure that phase delay by bringing it to something on the scale, so we can read the reading actually. So now if I go to, now I set it at 30 degrees, and there's an additional 7 degrees on this meter. That means the total phase difference is 37 degrees between the reference channel and the channel B that is that we have below here. And the amplitude, as you can see, is on this one reads minus 6.8 decibels or so on channel A, which is a reference, and channel B is down to minus 7.2, I would say, roughly. So it's slightly lost a bit of signal. 20 megahertz is not very high frequency for this cable, so I think that's probably reasonable. So I'm mostly interested in the phase. The amplitude is not going to drop very much for this type of cable. So the phase is now measured at minus 37.5 degrees, I would say. It's exactly halfway between 6 and 9 on the 18 degree scale, which is a lower scale. So that is 7.5 degrees on this one, plus the additional 30 degrees, so 37.5 degrees is the phase difference between channel A and channel B. Okay, I put the reference back, remove the cable and put the channel B back into the original position where there's no more cable. So I'm changed the frequency to now 40 megahertz, and essentially with 40 megahertz you should see twice the phase difference because it's double the frequency, so there's going to be more phase difference for a given delay or a length of cable. So now I've centered this one again, I believe, to 0 for and amplitude on A and B now are about the same. So now I'll put the cable back, and we'll take a look at the phase difference. Okay, so now again phase is the reading is gone off the scale. Try and bring it back into range. 50 degrees, 60 degrees, 70 degrees. So it's now 73, 74, 74.7 degrees. That's what I'm reading for this 40 megahertz signal, 74.7 degrees. I'm going to make a note of that, and then we'll do the calculations a little bit later. Okay, the third method I'm going to use to measure the phase of this 1 meter cable is using a lock-in amplifier. Lock-in amplifier is a instrument that is a very precise instrument that actually can measure the phase of any signal with respect to a reference signal. So this lock-in amplifier goes from very low frequencies like a few hertz up to 2 megahertz, and I'm going to use the highest frequency because I'm going to get the highest phase difference for a given cable length. I can use lower frequencies, but then the accuracy of the measurement is going to degrade as the phase difference will be small for low frequency. Right now, as you I have set the oscillator up for 2 megahertz, which is the highest frequency for this lock-in amplifier, and an amplitude of 100 millivolts, which I can apply from the oscillator to the channel A input, which is one of the voltage inputs for this lock-in. Right now this phase won't make any sense. There's no signal as either, so once I connect it, it should read 100 millivolts. So there you go. It's 100.2 millivolts. Phase is needs to be auto phase, so try and get it close to 0, which is good enough. And as you can see, the internal reference phase is 3.9 degrees. That means this particular cable is introducing some phase difference, which I don't want to trust because there's some internal phase differences within the instrument which I would like to avoid including in this. So what I'm going to do is to add another cable which is exactly 1 meter, so I would know that if this is a reference, adding another 1 meter cable would shift the phase exactly by the phase of 1 meter cable. So we'll do that next. Okay, so I've got another cable over here, which I'm going to just extend this one. I also changed the time constant to half a second, so there's less sensitivity to noise. It'll integrate over a longer time period. So now I'm going to put in this extra 1 meter cable and go back into this input, and now it's reading 3.90 degrees. So we'll make a note of that, and using this number we can calculate the phase difference of a 1 meter cable. So to do the calculations for the 3 methods, we'll start with the first method. We tried with the oscilloscope. We had 2 signals going into the oscilloscope. One was basically a reference clock, which was to set the edge for the triggering, and the other signal was going into the channel 2, which was the main signal we wanted to measure. And so we took those 2 cables and applied the 2 signals into the channel, 2 channels of the oscilloscope, and set the reference delay for that particular measurement. So we're not going to use that for the actual measurement, but we want to get a reference, and we got a reference delay for that as 21.55 nanoseconds. So that delay includes various delays within the AWG itself, plus cable mismatch delays, delays within the scope, all the systematic delays that were there in the setup. So once we got that out of the way, we calculated that as using a measure, using the cursors. We got 21.55 nanoseconds for that setup. Next, on the channel we wanted to measure, we introduced the 1 meter cable and added that to the original setup. So we got a new delay after that. The new delay with the 1 meter cable, D1, is 26.7 nanoseconds. So the difference in delay for the 1 meter cable is basically D1 minus D0, which is 5.15 nanoseconds. The second thing we did was the second method was the HP8405A, which was using that vector voltmeter. So let me zoom out so you can see the whole board here. Okay, so in this measurement we have this unique setup where we have 2 channels again in the HP8405, one of which takes a reference for locking in the internal signal to log to for the vector voltmeter, against which it compares the actual signal that is coming in. So we have a capability for this instrument to go all the way up to 1 gigahertz, but to keep the frequencies in the same ballpark as what we were doing earlier, I basically use lower frequency, so as frequency of 20 megahertz and 40 megahertz. Of course, these are sinusoidal signals, so the bandwidths these are actually narrow band signals, so measurements, so it's tuned for that particular frequency, so any inaccuracies or any harmonics or those type of effects are not in the measurement. The oscilloscope measurement of course requires sharp edges, which means you have a lot of high frequency components in the edges of those signals, so we need a good oscilloscope or a high frequency oscilloscope with high bandwidth to measure these sharp rise times to get a good delay number. But here, this being a RF instrument, it uses pure harmonics, that is a single first harmonic of the signal, which is the two frequencies we used here. So basically once we nulled out the channel A and B using the test fixture, all we had to do was to introduce the 1 meter cable, and for 20 megahertz we saw a phase difference of 37.5 degrees, and for frequency of 40 megahertz we saw a phase difference of 74.7 degrees. Now we have to convert these degrees basically into time. So first thing we have to do is to convert this into a wavelength. How many wavelengths of the signal are we talking about? So that is basically you divide 37.5 by 360 and then multiply by the period of the waveform. The sinusoidal signal in this case is 20 megahertz. So the period is 1 over the frequency, so the total delay for that delta phase of 37.5 degrees works out to 5.20 nanoseconds. For the 40 megahertz signal we got twice the amount of delay because the frequency was double. So now we got 74.7 divided by 360 divided by 40 to the power 6, 40 megahertz. So we got 5.188 nanoseconds. The final or third measurement we did to measure the delay of the 1 meter cable was using the lock-in amplifier, the signal recovery 7280, which has a 2 megahertz upper frequency limit. So we used that, fed the oscillator signal, 100 millivolt signal at 2 megahertz into the signal input and nulled that out using the auto phase feature, and we then added a 1 meter cable, measured the delay of that cable, and that came out to be 3.90 degrees. And as before, since this is a phase measurement, we have to convert that to basically time. So we basically take delta phase and divide by 360, which is one wavelength, and then multiply that by the t period, which is a time unit. So this is dimensionless, so we basically get a time unit at the end, that is 3.9 divided by 360 divided by 2 times 10 to the power 6, which is 2 megahertz, and that results in time of 5.42 nanoseconds, which is slightly larger than the previous measurements we got with the vector voltmeter and scope, but fairly good considering that this is a fairly small phase difference. And yeah, I think this was probably challenging for this measurement, but if it's a longer cable, I would say that this could be used fairly successfully without too much trouble. So let's now look at the final conclusions and the velocity of propagation results, and then end the video. Okay, we're almost done with this video, and let's go through the final results and do the velocity of propagation calculation. So we had the oscilloscope measurement where we got 5.20 nanoseconds for the delay of the 1 meter cable. I referred to that as a 3 feet cable at the beginning. I'm sorry about that. It's actually a 1 meter cable, which means there's a 3 inches longer 3 foot cable, 3.5, whatever. The vector voltmeter was an average measurement of 2 of the frequencies I did, so I got 5.194 nanoseconds for that. I'll use that for the calculation later. Lock-in was probably the least accurate given the frequency was fairly low for the measurement, and the delay was measurement came out to be 3.9 degrees. In fact, I noticed that later on after looking at the measurements that even using the single cable from the oscillator to the A channel, I was seeing a 3.865 degrees difference, which is basically correct actually without having to add an extra cable to do the measurement. So I assume that internally the phase, the delay between the reference and the signal channel is well accounted for. So we could potentially use that number 3.865, would get a slightly smaller number which agrees more closely with these other two numbers. Now speed of light, C is 3.83 times 10 to the power 8 meters per second, or 0.3 meters per nanosecond. The cable length is, as I said earlier, 1 meter. We'll use that as reference for us. It could be off by a centimeter or whatever, depending on the connector where they are connected and so on. But assume it's a 1 meter cable. Now the time for an electromagnetic wave, like a light signal or electrical signal travel in air or free space is going to be, for 1 meter, will be 3.333 nanoseconds. The velocity of propagation in RG316 for the 1 meter cable then therefore will be 3.333 divided by 5.194, which this number, times C, which is 0.642 C, or 64.2% of the speed of light in free space. So given the data sheet number is 69%, we are off by around 5%, which is a fairly good result given that this was a fairly quickly done measurement without averaging. The setup was fairly crude in a lot of respects. So given that, I think it's a good measurement to have gotten out of this 3, and if you take the average of these 3, you probably get roughly the right measurement. There are 3 different methods. Now the sources of errors, there are several of them. Number 1, of course, is the connectors. We have different connectors with different delays within them. They're not accounted for and they're not consistent among the measurements, so that's something to look out for. Number 2, the reflection, although given the fact that this was a fairly short cable and we had fairly good signal integrity, we wouldn't have to worry about reflection. But if we're dealing with very, very sharp edges over longer distances, we could see some effects of reflection that would change the delays significantly. Number 3, we have the measurement errors itself of the interpretation of the measurements, lack of averaging, human error, cable length, etc., with not being accurately represented basically. And number 4, there's also the bandwidth of the instruments. In the case of the oscilloscope, we are looking for edges, so we need sharp edges. High frequency components are important in there. But for the RF measurements, for the lock-in and for the vector voltmeter, there are signal amplifier related delays which could be different for different signal amplitudes. So if you do a lot of different measurements using different amplitudes, you would have to consider those. But here we had fairly large signals, so I think the delays in the instruments themselves would not be too bad. Lastly, we have the material differences. The fact that we are not using the datasheet device, we are using some other manufacturer. There could be some differences in the dielectric constant that would account for maybe a few percentage differences in the actual results. So that concludes this 3-part 3-way measurement for signal delays in a cable. Hopefully this was informative. Your comments are welcome. Any other source of error, any other things that you can think of, please mention that in the comments below. Look for you in the next video. Thank you.